Summer 2020, Berkeley, California, a university research program. A young undergraduate student named Shane Smith is sitting in front of a screen, going through data. He is not a senior researcher with decades of experience. He is a student from Hillsdale College in Michigan, participating in a summer research internship at the Berkeley SETI Research Center, a program supported by the National Science Foundation and the Breakthrough Listen initiative. He has been assigned a project. He is supposed to search a specific dataset for signals that match a specific set of criteria. The dataset he is searching was collected at the Parkes Murray-Young Radio Telescope in southeastern Australia. 64 meters of dish, one of the most storied radio astronomy instruments in the southern hemisphere. The data was recorded in April and May of 2019, over a year earlier. It was collected as part of a campaign to observe a nearby star for radioactivity. The target of the observations was Proxima Centauri, the nearest star to our Sun. Smith is running the data through an algorithm called Turbo SETI. The algorithm searches for narrowband signals concentrated in a tiny sliver of radio frequency that drift slightly over time in a pattern consistent with the Doppler effect, the kind of drift you would expect from a transmitter on a planet that is moving relative to Earth, its motion carrying it slightly toward or away from us, and shifting the observed frequency of any signal it emits. This is exactly the kind of signal that a radio transmitter aboard an extraterrestrial spacecraft or on the surface of an extraterrestrial planet would produce. The algorithm runs. The results come back, and there is a line, a narrow, diagonal streak, drifting slowly across the frequency-time plot, rising from lower frequencies to slightly higher ones over the course of the observation, at a rate consistent with Doppler shift from a planetary transmitter. Smith scrolls through the detection logs. The signal is at approximately 982 MHz. It is present during the periods when the telescope was pointed directly at Proxima Centauri. When the telescope nods away to check a reference position, the standard procedure used to eliminate terrestrial interference, the signal disappears. When the telescope returns to Proxima Centauri, it comes back. He looks at the signal for a long time. Then he contacts his supervisor. The supervisor contacts the Breakthrough Listen team. The team's reaction is immediate and measured. They do not celebrate. They do not make any announcements. They designate the signal BLC1. Breakthrough Listen Candidate 1, the first signal ever detected by the program to pass their initial screening criteria for a potential technosignature. And they begin, quietly, one of the most rigorous signal analysis processes in the history of the search for extraterrestrial intelligence. 6 months later, in December of 2020, the story leaks to the press. Within hours, it is everywhere. For a few weeks in December 2020, much of the world believed that we had found it, a signal from the closest star, from the nearest possible world, a signal that looked exactly like what an alien civilization might send. What happened next changed the search for extraterrestrial intelligence forever. Just not in the way anyone expected. The signal was real, the data was clean, the analysis was rigorous. Every test the Breakthrough Listen team ran, at first, came back with the same result. This signal looks like what we have been looking for, narrowband, on source, drifting, at a frequency not associated with any known natural process. From the direction of the nearest star, and the time it took to figure out what it actually was, produced something more valuable than a confirmed alien transmission. It produced a method, a framework for analyzing SETI candidate signals so rigorously that the same mistake, the mistake of holding a false positive for an extended period without recognizing it, could be caught far more quickly in the future. BLC-1 was not the discovery of alien life. It was the discovery of how to search for alien life without fooling ourselves. This video is about BLC-1. It is about the Parkes telescope in New South Wales, Australia, picking up a radio signal during observations in April and May of 2019 that would spend over a year sitting in archived data before anyone noticed it. It is about a summer student who noticed it, and about the team of scientists who spent the better part of 2 years rigorously and carefully figuring out what it was. It is about Proxima Centauri, the nearest star to our Sun, about 2 light-years away, host to at least 2 confirmed planets, one of which orbits in the habitable zone where liquid water could exist on the surface. And it is about what BLC-1 changed, not about the cosmos, not about alien civilizations, but about the methodology of one of the most ambitious scientific searches humanity has ever conducted. The signal itself was not alien. 2 papers published in Nature Astronomy in October of 2021 were clear. BLC-1 was terrestrial radio frequency interference, produced by a process called intermodulation that had passed the initial screening criteria of a sophisticated SETI program. The investigation that reached that conclusion, one of the most thorough analyses of a SETI candidate signal ever conducted, produced a verification framework that has since influenced the field's standards. That framework is the real legacy of BLC-1, not an alien contact, not a near miss with the most important discovery in human history, a better methodology, a more honest approach, a scientific community that, having been very nearly fooled by one of the most convincing false positives in the history of the search for extraterrestrial intelligence, strengthened its screening process so it would be better equipped next time. By the end of this video, you will understand exactly what BLC-1 was, why it looked so convincing, and how the investigation that ruled it out became one of the most important contributions to SETI methodology in years. You will understand what we know about Proxima Centauri b, the nearest habitable zone planet, and why its habitability is genuinely uncertain in ways that matter. And you will understand why the BLC-1 story, honestly told, is more interesting and more important than either the alien hype version or the dismissive nothing to see here version. So, what exactly was BLC-1? Why did it look so much like what an alien signal should look like that even the scientists who found it took the better part of 2 years to rule it out? Why was it only present when the telescope was pointed at Proxima Centauri? If it was terrestrial interference, why did it behave like it came from space? What is Proxima Centauri b, and is it actually habitable? And if something is living there, would we be able to detect it with the instruments we have right now? What does it mean for the SETI program that the most convincing candidate signal in decades turned out to be interference? And how does the methodology that BLC-1 forced the field to develop change how we will handle the next candidate? And what has JWST been finding in the last 2 years about the Centauri system, the nearest stellar neighborhood to our own, that changes the picture of where life might exist in our cosmic backyard? This is not a video about confirmed alien contact. BLC-1 was not an alien signal. The Breakthrough Listen team was clear about this in 2021, and there have been no developments since that changed that conclusion. If you came here hoping for confirmation that we have found extraterrestrial intelligence, this is not that video. But this is also not a video that dismisses BLC-1 as a simple mistake or a non-event. The investigation the Breakthrough Listen team conducted to rule out BLC-1 was one of the most rigorous and scientifically productive signal verification processes ever undertaken in SETI. The framework it produced, The methodology for how to analyze and verify SETI candidate signals has shaped the field standards, and the broader story of Proxima Centauri, its planets, and its near neighborhood is genuinely extraordinary. New findings from JWST about the Alpha Centauri system, just over 4 light-years away, are still being processed. The nearest star has a planet in its habitable zone, and we do not yet know whether that planet has an atmosphere. What we will do in this video is trace the actual scientific story, from the detection, through the patient investigation, to the methodology that emerged from one of the most important false positives in SETI history. The truth, when told properly, is more interesting than either the alien hype version or the dismissive version. Stay with me. Quick pause. If these are the kinds of stories that pull you in, real SETI science told honestly without the hype and without the dismissal, hit subscribe. Galaxy Pulse goes beyond the headlines every single time. Now, back to Proxima Centauri and the star that is close enough to matter. To understand why BLC-1 was so significant, and why the investigation that ruled it out matters even more than the signal itself, we need to understand the target. Proxima Centauri is not just the nearest star to our Sun. It is the closest possible location for an inhabited world. It is the star toward which the first interstellar probe, if we ever build one, would most likely be aimed. And it is a star that, before BLC-1, was not particularly well understood in terms of whether it could support the kind of life we know how to look for. The signal changed that, not by confirming life, by focusing scientific attention on Proxima Centauri more sharply than ever before. The nearest star to our Sun is not, by any obvious measure, a promising place for life. Proxima Centauri is a red dwarf, spectral class M5. It has approximately 1/8 the mass of the Sun, and produces only a tiny fraction of the Sun's luminosity, roughly a 600th of the light, at the same distance. To receive Earth-equivalent illumination, a planet would have to orbit Proxima Centauri about 20 times closer than Earth orbits the Sun. It is worth pausing on what kind of star this actually is. Because red dwarfs are the most common stars in the galaxy, and understanding them is central to understanding where life might exist in the universe. Red dwarfs make up something like 70 to 80% of all the stars in the Milky Way. They are small, cool, and extraordinarily long-lived. A red dwarf like Proxima Centauri will continue burning hydrogen for trillions of years, far longer than the current age of the universe, and vastly longer than the roughly 10 billion years a Sun-like star can sustain. If habitability is partly a function of how long a star provides stable conditions, red dwarfs offer an almost unimaginable span of time for life to develop. But that longevity comes with a cost. Red dwarfs are small enough that their habitable zones, the range of orbital distances where a planet could maintain liquid water, sit very close to the star, and close orbits around a magnetically active star mean exposure to conditions that are far harsher than anything Earth experiences. This tension, long-lived stability on one hand, severe radiation and tidal effects on the other, is the central question of red dwarf habitability, and Proxima Centauri sits right at the heart of it. For most of the 20th century, the close-in habitable zone was considered essentially disqualifying for habitability. Any planet close enough to receive adequate light from such a dim star would be so close that the star's gravity would synchronize the planet's rotation with its orbit, tidally locking it so that one face always faced the star and one always faced away. The illuminated face would be scorching, the dark face would be frozen. The terminator zone between them might be habitable, but the atmospheric and oceanographic dynamics of a tidally locked world were considered deeply unfavorable. Then the models got better. Three-dimensional atmospheric simulations in the 2010s showed that tidally locked planets could, under the right conditions, distribute heat effectively through atmospheric and oceanic circulation, maintaining temperatures across much of their surfaces that were compatible with liquid water. The picture became more nuanced. Tidally locked worlds in the habitable zone of red dwarf stars were no longer automatically ruled out, and then came the discovery of Proxima Centauri b. In August of 2016. A team led by Guillaume Anglada-Escudé at Queen Mary University of London announced the detection of a planet orbiting Proxima Centauri. The detection method was the radial velocity technique, measuring the tiny wobble that the planet's gravitational pull induces in the star's motion, visible as a periodic Doppler shift in the star's spectrum. The data, collected primarily with the HARPS spectrograph at the European Southern Observatory in Chile, was unambiguous. The planet's minimum mass was approximately 1.3 times the mass of Earth. Its orbital period was 11.2 days. Its orbital distance was approximately 0.05 astronomical units, 20 times closer to its star than Earth is to the Sun, but in the habitable zone because the star is so much dimmer. This was extraordinary. The nearest star to our Sun, a star that had been observed for decades, had a planet in its habitable zone, not a gas giant, not an ice giant, a roughly Earth-mass world, possibly rocky, possibly water-rich, orbiting at precisely the distance where liquid water could exist on its surface if it had the right atmosphere. It is worth understanding how hard this detection actually was, because it speaks to why the Centauri system has been so difficult to study. The radial velocity method detects a planet by measuring the tiny back-and-forth wobble it induces in its star. For Proxima b, that wobble corresponds to a change in the star's velocity of only about a meter per second, roughly walking speed. Detecting a shift that's small in the light of a star more than 4 light-years away, against the noise introduced by the star's own magnetic activity and surface convection, required years of careful observation and sophisticated statistical analysis. The Anglada-Escudé team's announcement was the culmination of a dedicated campaign called Pale Red Dot, specifically designed to settle the question of whether Proxima Centauri had a planet. The discovery triggered an explosion of scientific activity. Papers appeared studying every aspect of Proxima b's potential habitability. The atmospheric loss rate from stellar wind pressure, the magnetic field evolution, the tidal locking dynamics, the potential for biosignature gases to accumulate in a thick atmosphere, the possibility of life persisting under the intense ultraviolet and X-ray radiation from the star's frequent flares. It is also worth noting that Proxima Centauri is now known to host more than one planet. A second planet, Proxima Centauri c, was identified through continued radial velocity monitoring, a more distant, more massive world, far outside the habitable zone and far too cold for liquid water on its surface. There have also been indications of a third, smaller candidate, Proxima d, orbiting even closer to the star than Proxima b. The nearest star, in other words, hosts a genuine planetary system, not a single isolated world, but a family of planets, of which Proxima b is the one that happens to fall in the habitable zone. Here is the important complication, and it deserves its own moment. Proxima Centauri is not just dim, it is violent. Red dwarfs are among the most magnetically active stars in the galaxy. Despite their small size and low luminosity, they produce stellar flares, sudden, intense releases of electromagnetic radiation and charged particles, with a frequency and intensity that, relative to the star's baseline output, dwarfs what the Sun produces. Proxima Centauri is a particularly active example. It produces superflares regularly, eruptions that release far more energy relative to the star's normal output than the most powerful solar flares. Proxima b, orbiting so close, receives the full brunt of these events. During a superflare, the ultraviolet radiation reaching Proxima b increases by orders of magnitude. The charged particle flux, the stream of energetic protons and electrons that accompanies major flare events, is intense enough that, without a substantial magnetic field and atmosphere to deflect and absorb it, it would tend to strip the surface of complex organic molecules and make the maintenance of stable biochemistry very difficult. Whether Proxima b has the magnetic field and atmosphere needed to survive this radiation environment is unknown. It does not transit its star from our vantage point, so we cannot use the transit spectroscopy method to study its atmosphere. Indirect arguments provide some guidance, but they cut both ways. Some models suggest the atmosphere could survive. Others suggest it has been stripped long ago. This was the scientific backdrop: extraordinary proximity, genuine habitable zone status, severe radiation challenges, deep uncertainty, when the Breakthrough Listen program decided to point the Parkes telescope at Proxima Centauri in April of 2019. And it was into this backdrop that BLC-1 appeared. Under normal conditions, in a typical SETI survey, here is what the Breakthrough Listen team expects to find when it points a radio telescope at a nearby star. Background noise. The broad, smooth radio emission of the galaxy. Occasional narrow spikes from known terrestrial interference sources, ground-based radar, satellites, electronic equipment near the telescope, and, very rarely, candidate signals that pass the initial screening criteria for a Technosignature and are then followed up, almost always to be explained as some form of interference. In over a year of archived data from the Parkes telescope, covering many observed targets, one signal had survived the initial screening for a SETI candidate. And it came from the nearest star to our Sun. The properties of BLC-1, when Shane Smith pulled it from the data in the summer of 2020, were striking in every detail. The frequency, approximately 982 MHz. Not a frequency associated with any known natural astrophysical emission process. The drift rate. The signal was drifting slowly to higher frequencies over the course of the observation. This drift was consistent in direction and magnitude, with the Doppler shift expected from a transmitter on a planet orbiting a star, as the orbital motion of the planet carried it slightly toward Earth and shifted the observed frequency upward. The bandwidth, extraordinarily narrow. The narrowest natural cosmic radio sources have bandwidths orders of magnitude larger than this. A signal this narrow is, by the physics of electromagnetic emission, an indicator of an artificial transmitter, specifically, an oscillator that produces a very precise frequency rather than the broad spectrum of natural thermal or non-thermal processes. The on-source behavior, present when the telescope was pointed at Proxima Centauri, absent when the telescope was nodded to a reference position offset from the star. This is the most important behavioral characteristic for distinguishing celestial signals from terrestrial interference. Terrestrial signals, radio towers, satellites, electronic equipment are usually present regardless of where the telescope is pointed. Celestial signals come only from the direction of the source. The observing technique that produced this on-source, off-source pattern is worth explaining, because it is central to why BLC-1 was taken seriously. The Parkes campaign used a method sometimes called nodding or position switching. The telescope points at the target star for a few minutes, then swings to a nearby empty patch of sky for a few minutes, then back to the target, and so on, alternating throughout the observation. The logic is simple. A real signal from the star should appear only during the on-target segments and vanish during the off-target segments. A signal from a radio tower on Earth, by contrast, should be present the whole time, regardless of where the dish is aimed, because the tower is not in the sky at all. BLC-1 followed the on-target pattern. It appeared when Parkes looked at Proxima Centauri and faded when Parkes looked away. By the standard logic of the nodding technique, this was exactly the behavior of a genuine celestial source. It was, in retrospect, the single most misleading property of the signal, because intermodulation interference, produced by equipment whose behavior happened to correlate with the observing cadence, could mimic this pattern without coming from the sky at all. BLC-1 appeared to come only from the direction of Proxima Centauri. The gap between what a routine SETI dataset normally contains and what BLC-1 appeared to be was not subtle. BLC-1 had, by every criterion used in the field's initial screening process, many of the hallmarks of a genuine technosignature. The Breakthrough Listen team knew this. They also knew that extraordinary claims require extraordinary evidence. And so they began the investigation that would occupy much of the next 2 years. The story of how BLC-1 was discovered is, in a sense, a story about the infrastructure of modern science. The Parkes telescope had collected the raw data in April and May of 2019 during a campaign on Proxima Centauri led by Andrew Zick, then a PhD student at the University of Sydney. The campaign was studying stellar flare activity, the radio bursts produced by Proxima Centauri's intense magnetic activity, as part of a broader study of how flares from red dwarf stars affect the habitability of their planets. The radio data was being analyzed in the context of SETI as part of a collaborative arrangement with Breakthrough Listen. That radio data sat on a server for over a year, not because anyone was hiding it, because scientific data accumulates faster than scientists can analyze it. Breakthrough Listen collects more data per hour of observing than most humans can meaningfully process. The Turbo SETI algorithm exists precisely to automate the screening process, to do in seconds what would take a human researcher weeks to do by hand. The scale of the data problem in modern SETI is genuinely staggering, and it is worth understanding because it explains why a signal from the nearest star could sit unnoticed for over a year. A single observing session with a modern radio telescope, recording across a wide range of frequencies at high time resolution, can generate terabytes of raw data. Breakthrough Listen, observing many targets across multiple telescopes, accumulates this data faster than any team of researchers could ever examine it by eye. The bottleneck in SETI is no longer collecting data. It is processing it, screening it, and reviewing the candidates that automated screening produces. This is a profound shift from the early decades of the search. The first SETI experiments in the 1960s involved listening to a handful of frequencies from a handful of stars, with researchers able to examine essentially all of the data they collected. Modern SETI is the opposite. A flood of data so vast that the central challenge is building algorithms capable of finding the rare interesting signals within it, and then finding the human time to review what the algorithms flag. BLC-1 sat in the archive not because it was unimportant, but because it was one candidate among an enormous volume of data waiting for human attention. But Turbo SETI requires someone to run it on each dataset, to check the outputs, to review the candidates that emerge. And that requires human researchers, with limited time, working through a backlog of observations from multiple telescopes on multiple targets. Shane Smith was assigned to the Proxima Centauri dataset in the summer of 2020 as an undergraduate research project. He ran the algorithm. BLC-1 came out. He had been working on the project for about 2 months when it appeared. His reaction, as he later described it, was not immediately excited. He was new to the field. He did not immediately understand the full significance of what he was looking at. He showed it to his supervisor, who recognized it more quickly. The supervisor contacted the full Breakthrough Listen team. There is something quietly fitting about the fact that it was an undergraduate intern who found BLC-1. SETI has always depended heavily on students, early career researchers, and even citizen scientists to work through the volume of data the field produces. Both Shane Smith, who found the signal, and Sophia Sheikh, who led the investigation that resolved it, were early in their careers when they did this work. Smith, an undergraduate intern, Sheikh a graduate student. The most significant SETI candidate in years was found and resolved largely by people at the beginning of their scientific lives. That is not a coincidence. It is how the field actually works. The team's recognition was rapid. They ran BLC-1 through their standard set of initial screening tests. The signal was narrowband. It passed. The signal was drifting at a rate consistent with Doppler shift from a planetary transmitter. It passed. The signal was present on source and absent off source. It passed. The signal was not obviously present in data from other nearby stars observed in the same sessions. It passed. No known satellite or aircraft was immediately identified as a plausible source. It passed. No known natural astrophysical mechanism could easily explain a signal this narrow drifting at the observed rate. It passed. BLC-1 had passed the initial screening tests in the Breakthrough Listen pipeline. The team did not make an announcement. They kept analyzing. They assigned Sophia Sheikh, at the time a PhD student at Penn State, later a postdoctoral researcher at UC Berkeley, and then the SETI Institute, to lead the detailed follow-up investigation. Sheikh began developing what would become one of the most rigorous SETI signal verification frameworks ever published. And the team continued their work, hoping to complete their analysis before the story became public. In December of 2020, it leaked. The press published an account of the signal. The story specified enough details: the rough frequency, the drift, the on-source behavior, the target star, that it was immediately clear to anyone following SETI research that the Breakthrough Listen team had found something. The media cycle exploded. Headlines appeared in dozens of languages. The social media discourse was, predictably, dominated by alien speculation. The Breakthrough Listen team issued a careful statement. They neither confirmed nor denied alien origin. They stated that the signal was under investigation and that more analysis was needed before any conclusions could be drawn. They noted that candidate signals identified in SETI surveys were typically explained as interference. The public did not hear the careful statement. They heard the headlines. And, for a few weeks in December 2020, the question of whether we had made first contact with an extraterrestrial civilization, the question that humans had been asking since we first understood what the stars were, seemed, to many millions of people around the world, to have been answered. Let us slow down and make the physics here concrete. Because the rest of this story depends on understanding a few things precisely. What SETI actually looks for, what made BLC-1 look so convincing, and what the specific technical explanation for it revealed about the limits of the field's methodology. Think of it this way. Imagine you are listening for a specific kind of sound in a noisy room. The sound you are listening for has very specific properties. It is a pure tone, a single musical note, not a chord. It is drifting very slightly in pitch over time, the way a note from a moving instrument would drift as the instrument moves toward or away from you. The Doppler effect. The same reason an ambulance siren sounds higher when it is approaching and lower when it is moving away. And it is coming from one specific direction, a direction that, if the sound is real, corresponds to the source you are searching. Now, imagine you hear exactly that sound. Exactly the right kind of tone, extremely narrow in pitch, not a broad hum, exactly the right kind of drift, exactly the right direction. And when you look away from the direction the sound is supposedly coming from, it disappears. What do you conclude? Before you conclude anything, you need to check every possible alternative explanation. Every other instrument in the room that could be making that sound. Every way that two or more different sounds could be combining to produce what sounds like a single pure tone from a specific direction. Every electronic artifact of your listening equipment that could mimic the properties of the sound you are hearing. That is the work of SETI signal verification. And that is what BLC-1 looked like, and what the Breakthrough Listen team spent the better part of 2 years doing. There are 3 things you need to understand to follow what comes next. The first is what a technosignature is, and specifically, what property makes radio technosignatures unique. A technosignature is any signal whose properties are inconsistent with natural processes and consistent with artificial origin, specifically with the operation of a technology. For radio SETI, the primary technosignature property is narrowband emission. Natural cosmic radio sources, thermal emission, synchrotron radiation, maser emission, produce signals spread across a range of frequencies. An artificial radio transmitter, built around an oscillating electronic circuit, produces a signal concentrated in an extremely narrow frequency range. In the most precise modern transmitters, just a few hertz wide. It helps to understand why narrowband emission is such a reliable signature of technology. In nature, producing radio waves almost always involves processes that spread energy across a broad range of frequencies. The thermal jostling of hot gas, the spiraling of electrons in magnetic fields, the broad emission of molecular clouds. To concentrate radio energy into a sliver only a few hertz wide requires a precise, stable oscillator. The kind of device that human radio engineers build, and the kind of device that any technological civilization would likely also build, because the laws of electromagnetism are the same everywhere. A narrowband signal is, in effect, a fingerprint of deliberate engineering. This is why SETI has focused on narrowband emission since the field's earliest days in the 1960s. BLC-1 was extraordinarily narrow. In a radio telescope that can observe millions of frequency channels simultaneously, a signal a few hertz wide is a needle in a haystack, and it is exactly what an artificial transmitter looks like. The second is the Doppler drift signature. A transmitter on the surface of Earth, or on a satellite in Earth orbit, is moving relative to the Parkes telescope as the Earth rotates and the satellite orbits. This motion, Doppler shifts the observed frequency of the transmitter's signal, shifting it up or down depending on whether the source is moving toward or away from the receiver. A transmitter on a planet orbiting a distant star would also Doppler shift its signal, but in a characteristic way determined by the planet's orbital velocity and the geometry of the observation. For a planet in the habitable zone of a red dwarf, the expected drift rate is small but measurable. The drift is, in a sense, the signature of planetary motion written into the frequency of the signal. A signal from a transmitter sitting still on Earth would drift differently from a signal from a transmitter riding on a rotating, orbiting planet light years away. BLC-1 drifted at a rate consistent with a planetary transmitter. This was one of its most compelling properties. The third is the on-source versus off-source test. SETI surveys routinely observe a target star and then move the telescope slightly off the target to check a nearby reference region. This test is designed to catch terrestrial interference, signals that come from Earth rather than from the sky. Terrestrial signals are usually present regardless of where the telescope is pointed. Genuine celestial signals disappear when the telescope moves off the source. BLC-1 passed this test. When the Parkes telescope moved off Proxima Centauri, the signal was not obviously detected. All three of these properties, narrowband, drifting, on source only, were, in combination, the reason BLC-1 was taken seriously. They are the specific properties that SETI methodology, built over decades of theoretical work and observation, predicted that an alien signal would have. And they are the specific properties that BLC-1 displayed. So here is where the stakes rise in a way that goes beyond any individual signal. If BLC-1 had been confirmed, if the investigation had found no terrestrial explanation, if the signal had recurred in follow-up observations, if the Breakthrough Listen team had been forced to say, publicly and officially, that they had found a signal from Proxima Centauri that could not be explained as interference, the implications would have been impossible to overstate. It would have been, potentially, the confirmation of the existence of extraterrestrial intelligence, not just life, intelligence, a civilization capable of building a radio transmitter, operating it on a specific frequency, and doing so for long enough that we caught a fragment of its transmission from over 4 light-years away, at the nearest star to our sun, at the place where the first interstellar probe, if we ever build one, would go. Everything would have changed, not just astronomy, not just science, everything. The philosophical implications of confirmed alien intelligence, the resolution of the Fermi paradox, the transformation of our understanding of our place in the universe, the immediate and profound challenge to every religious, cultural, and philosophical framework that assumes human intelligence is unique, are beyond the scope of any single paragraph. But they are real, and the people working at Breakthrough Listen in 2020 understood them perfectly well. They also understood what would happen if they announced a discovery and then had to retract it. The history of science includes premature announcements that damaged the credibility of the scientists who made them and the fields they worked in: cold fusion, faster-than-light neutrinos, arsenic-based life. Each of these stories followed a similar pattern: a dramatic announcement, a wave of public excitement, a period of failed replication, a quiet withdrawal of the original claim. For SETI, a false announcement of alien contact would be especially damaging. It would not just damage the credibility of the individual team, it could set back the entire scientific project of searching for extraterrestrial intelligence by years. This is why the Breakthrough Listen team did not announce BLC-1 when Smith found it in the summer of 2020. This is why they continued analyzing, quietly, before the story leaked. And this is why the investigation they conducted, one of the most rigorous SETI signal analyses ever published, matters so much more than the signal itself. Because the stakes of getting it wrong were, in a field that is already fighting for scientific credibility, almost as high as the stakes of getting it right. The investigation of BLC-1 was unlike anything SETI had previously attempted at this level of rigor. Previous candidate signals, and there had been several over the decades, none as convincing as BLC-1, but a number that had generated short-term interest, had typically been handled through a relatively straightforward process. Search for recurrences, check against known interference databases, look for the signal in other datasets. If it doesn't recur and doesn't match any known source, classify it as unexplained and move on. BLC-1 was different. Its properties were too specific, too clean, and too consistent with theoretical predictions for the team to apply only a routine process. Sophia Sheikh, assigned as lead analyst, recognized that a candidate of this quality required a framework, a systematic, documented, peer-reviewable procedure for exhausting every non-alien explanation before any conclusion could be drawn in either direction. She built one. The framework Sheikh developed proceeded in a series of steps, each designed to eliminate a specific class of alternative explanation. The first step was the most basic. Search for the signal in observations of other targets from the same sessions. Terrestrial interference sources, radio towers, electronic equipment, satellite transmissions, produce signals that are not tied to a specific celestial direction. If BLC-1 was from Proxima Centauri, it should not appear in data collected when the telescope was pointed at other targets during the same night of observing. BLC-1 did not obviously appear in other targets. That was consistent with a celestial origin. The second step was to check for recurrences in follow-up observations. Breakthrough Listen conducted additional hours of observation of Proxima Centauri, 39 hours in total across multiple sessions, specifically searching for BLC-1 at its original frequency and drift rate. A real transmitter from Proxima Centauri, if it was continuously broadcasting or even operating on a schedule, should eventually reappear. BLC-1 did not recur. That was not consistent with a continuously operating transmitter, but it was also not decisive, since a civilization might broadcast intermittently. The third step, and the one that ultimately resolved the case, was the harmonic analysis. Sheikh searched the full dataset, all of the Proxima Centauri observations from the original Parkes campaign, for signals at frequencies harmonically related to BLC-1 frequency. The reasoning was specific. A process called intermodulation occurs when two or more radio frequency interference sources are present and their signals mix together in a nonlinear electronic element, a poorly shielded amplifier, a corroded connector, an overloaded circuit. Intermodulation produces new signals at frequencies that are combinations of the original source frequencies. If BLC-1 was an intermodulation product, there should be other signals in the data at frequencies that are harmonically related to the sources that produced it. There were. Sheikh found dozens of signals in the Parkes dataset with morphologies, drift rates, narrowband properties, on-source behavior, similar to BLC-1. They were clustered at frequencies harmonically related to BLC-1 frequency. Specifically, they appeared at frequencies consistent with the kind of clock oscillators found inside computers, laboratory instruments, and other electronic equipment. This was the resolution. BLC-1 was an intermodulation product. Two or more sources of radio frequency interference in or near the Parkes facility. Sources whose individual frequencies were unremarkable and easily screened by the standard interference filters, were combining in a nonlinear electronic element somewhere in the signal chain, producing a new signal near 982 MHz. The new signal inherited the narrowband properties of its parent oscillators. Its apparent drift was produced not by Doppler effect from a moving planet, but by slow, electronic frequency variation in one or both of the parent sources. Its on-source behavior, its appearance and disappearance correlated with telescope pointing, was likely tied to the timing of the observing cadence rather than to anything in the sky. It is worth dwelling on why intermodulation is such a treacherous source of false positives. Because the mechanism is genuinely counterintuitive. Most people think of radio interference as something obvious, a loud signal at a known frequency, easily recognized and filtered out. Intermodulation is different. It does not appear at the frequency of any actual transmitter. It appears at a new frequency, created by the mathematical combination of two or more original frequencies, when those signals pass through a component that responds in a nonlinear way. A clean, electronic component passes signals through unchanged. A nonlinear one, an overdriven amplifier, a corroded connector acting as an accidental diode, a saturated circuit, mixes them together and produces sums and differences of the original frequencies. This means that two perfectly ordinary, individually harmless interference sources, neither of which would ever be flagged as a SETI candidate, can combine to produce a signal at a completely different frequency that does look like a candidate. The parent signals might be at frequencies that are obviously terrestrial and routinely filtered. The intermodulation product they create can land in a clean part of the spectrum, far from its parents, wearing the disguise of a narrowband, drifting, on-source signal. This is precisely what makes intermodulation so dangerous for SETI. It manufactures false positives that look nothing like their actual terrestrial sources. The conclusion, stated plainly in the Sheikh et al. Paper published in Nature Astronomy in October 2021. BLC-1 is not an extraterrestrial technosignature. It is, in their words, an electronically drifting intermodulation product of local, time-varying interferers aligned with the observing cadence. There is a nice analogy that Sheikh herself has used to explain intermodulation. If you have ever heard an electric guitar played through an overdriven amplifier, the warm distortion of rock and blues, you have heard intermodulation. When the amplifier is pushed beyond its clean range, the different frequencies in the signal mix together and produce new tones that were not in the original. BLC-1 was, in a sense, the radio equivalent of that distortion, an artifact of electronics being pushed in a way that produced a signal that was not really there as a single coherent source. The investigation took the better part of 2 years, 39 hours of follow-up observations, a systematic harmonic search, a published framework, and a result that was, in the most literal sense, a scientific contribution, not because it found aliens, but because it produced knowledge that the field did not have before. A negative result had expanded the field's knowledge of what to look for. The 2 papers published in October 2021 did not make the news the way the December 2020 leak had. There were no viral headlines, no breathless social media posts about the implications for humanity. A handful of science journalists covered the resolution carefully and accurately. Most of the public either did not see it or saw it and moved on, having already absorbed the initial story as one of the interesting things that happened that year. This is a pattern that science communicators have long recognized and long struggled with. The exciting claim gets attention. The careful correction gets almost none. The public ends up with a distorted picture. In this case, a vague impression that something interesting had been detected near Proxima Centauri, which is true, combined with no clear sense of what the careful investigation had actually revealed, which is unfortunate. Because what the investigation revealed was, for the SETI field, genuinely significant. The pre-BLC-1 breakthrough listen methodology was built around a set of screening criteria that were theoretically well motivated. Narrowband emission, Doppler drift at a rate consistent with a planetary transmitter, on-source presence, absence from data collected at other targets. These criteria were drawn directly from the theoretical literature on what artificial radio signals would look like. They represented the best available thinking about how to distinguish alien signals from natural and terrestrial sources. BLC-1 passed all of them, and it was terrestrial interference. This meant that the screening criteria, however theoretically motivated, were insufficient on their own. They could be fooled, not by some exotic, unforeseeable mechanism, but by a specific class of interference that was physically plausible, experimentally reproducible, and present in real telescope data. The Sheikh framework addressed this gap directly. Its central addition to the screening process was the harmonic analysis, the systematic search for signals at harmonically related frequencies that would identify intermodulation products before they could be mistakenly classified as candidates. This single step, if it had been applied to BLC-1 when Smith first found it, would likely have identified it as an intermodulation product much sooner. The broader principle that the shake framework encodes is worth articulating clearly. A candidate signal should not be considered credible simply because it passes a set of theoretically motivated positive criteria. It must also be tested against a systematic catalog of known interference mechanisms, including mechanisms that produce behavior specifically designed to mimic the positive criteria. The burden of proof for a SETI candidate is not just, does this look like an alien signal, but, have we demonstrated that it cannot be explained by any known non-alien mechanism? Those are very different standards, and BLC-1 demonstrated, in practice and with real data, why the difference matters. There is a parallel worth drawing here that the BLC-1 experience makes very clear. In our video on the WOW signal, if you have watched it, we discussed the decades-long effort to explain a signal detected in 1977, where the leading recent hypothesis points toward a natural astrophysical phenomenon rather than an alien transmission. The WOW signal represented the opposite challenge from BLC-1. It was a genuine, unexplained detection, a signal that did not obviously fit any known interference mechanism, and it took decades of patient archival work to develop a plausible natural explanation. BLC-1 was a convincing false positive, a signal that looked artificial but was terrestrial, identified and explained in roughly 2 years by rigorous methodology. Together, the WOW signal and BLC-1 define the two fundamental challenges of SETI signal verification. The first is the challenge of the genuine anomaly, a signal that doesn't look like interference but might be natural or might be a one-off that can never be re-examined. The second is the challenge of the convincing fake, a signal that looks exactly like what you are searching for but is terrestrial. The shake framework was built to address the second challenge. Both the WOW signal investigations and the BLC-1 investigation were products of patient, rigorous, honest science that refused to take shortcuts. There is also a harder question that BLC-1 raises, and that the field has not yet fully answered. If BLC-1 could pass the breakthrough LISTEN screening, one of the most sophisticated SETI screening pipelines ever deployed, what else might be passing it right now? How many other candidate signals in the field's archives are intermodulation products that happen to fall outside the frequencies where the harmonic check was applied? And more fundamentally, is the existing methodology robust enough to handle a real signal if one is detected? This question is taken seriously within the SETI community. It has not been fully resolved. It is one of the active areas of methodological research that BLC-1 directly stimulated. The field that existed before BLC-1 was found was, arguably, more confident in its methodology than the evidence warranted. The field that emerged from the investigation of BLC-1 is more honest about its limitations, and, because of that honesty, better equipped to handle the next candidate. Before BLC-1, Proxima Centauri b was an interesting exoplanet. After BLC-1, it became one of the most intensively studied objects in the solar neighborhood. The signal, even though it was not alien, focused scientific attention on the Centauri system in a way that changed the research landscape. Papers on Proxima b's habitability multiplied. Observations of Proxima Centauri's flare activity, stellar wind, and magnetic environment increased. The question of whether Proxima b could support life stopped being a theoretical exercise for a small community of specialists and became a mainstream topic in astrobiology and planetary science. What emerged from that focused attention was a picture of extraordinary complexity. A planet that cannot be simply described as habitable or uninhabitable, Because the answer depends on conditions we do not yet know. Start with what we do know. Proxima b orbits in the habitable zone of its star. This is not in dispute. At its orbital distance from a star, with a tiny fraction of the Sun's luminosity, the equilibrium temperature of a planet with Earth-like reflectivity is in the range where liquid water could exist on the surface. The habitable zone calculation is straightforward physics, and Proxima b satisfies it. Proxima b has a minimum mass of 1.3 Earth masses. This is consistent with a rocky planet, a world with a solid surface, potentially with internal geology, potentially with the kind of geothermal heat that could support subsurface liquid water even without stellar illumination. It is also consistent with other compositions. We do not know which. Proxima b is almost certainly tidally locked. At its orbital distance from a red dwarf, the tidal forces are strong enough to synchronize the planet's rotation with its orbital period. This means one face of the planet permanently faces the star and one permanently faces away. This used to be considered a showstopper for habitability. The models have changed. Three-dimensional climate simulations of tidally locked terrestrial planets in the habitable zones of red dwarfs have, over the past decade, repeatedly shown that atmospheric circulation can effectively distribute heat from the day side to the night side, preventing the night side from freezing out entirely and the day side from becoming a runaway greenhouse. The temperature gradient between the two hemispheres is large, but not necessarily so large as to preclude liquid water in a broad band near the terminator, the boundary between permanent day and permanent night. These models have also shown that the specific atmospheric composition matters enormously. A thick carbon dioxide atmosphere can provide both the greenhouse warming needed to maintain liquid water temperatures and some of the ultraviolet shielding needed to protect surface chemistry from the star's intense radiation. Now, consider the most serious challenge: the flares. Proxima Centauri produces superflares multiple times per year. During a superflare, the ultraviolet radiation reaching Proxima b increases dramatically. The charged particle flux from the accompanying stellar energetic particle event could, without substantial atmospheric protection, directly damage surface organic chemistry and potentially erode the atmosphere over geological time. The scale of these flares is genuinely striking. In 2019, astronomers observed a flare from Proxima Centauri that, for a brief period, made the star roughly 14,000 times brighter in ultraviolet light than its normal output. A flare of that magnitude, hitting a planet orbiting as close as Proxima b does, delivers a dose of radiation to the planet's upper atmosphere that has no equivalent in Earth's experience. The Sun does produce flares, and large solar storms can disrupt satellites and power grids on Earth. But the Sun's flares are modest compared to the star's overall brightness. Proxima Centauri's superflares represent enormous spikes relative to a dim baseline, and they happen far more often than comparable events on the Sun. This matters for habitability in two distinct ways. The first is the immediate question of whether life on the surface could survive the radiation. The second, and possibly more important, is the long-term question of whether the atmosphere itself can survive. Over hundreds of millions or billions of years, repeated flaring and the accompanying stellar wind can strip away a planet's atmosphere, particularly if the planet lacks a strong magnetic field to deflect the charged particles. A planet with no atmosphere is not habitable in any conventional sense, regardless of its temperature or its position in the habitable zone. Research published in 2020 examined the UV surface habitability of Proxima b by constructing models of different atmospheric compositions and measuring the UV flux reaching the surface through each. The result was not as discouraging as might be expected. Thick carbon dioxide and nitrogen atmospheres provided sufficient shielding from the most damaging UV wavelengths that surface biochemistry could potentially survive even during major flare events. If life had adapted to intermittent high radiation periods, there is also an intriguing possibility that the flares, while threatening, are not purely destructive. Some researchers have suggested that the ultraviolet radiation from red dwarf flares could, under certain conditions, drive the kind of chemistry that produces the building blocks of life, the prebiotic chemistry that may have been important in life's origins on Earth. The relationship between red dwarf activity and habitability may not be a simple matter of more flares being worse. It may be more nuanced, with flares playing both destructive and potentially constructive roles depending on the planet's atmosphere and the stage of its development. This is not the same as saying Proxima b is habitable. It is saying that specific atmospheric conditions could make it habitable, and that the relationship between the star's violence and the planet's potential for life is more complex than it first appears. Whether the necessary conditions exist is the question that remains open. And here is the most important thing to understand about Proxima b's habitability status. We cannot fully answer this question with current instruments. Proxima b does not transit its star from our perspective. We cannot use transit spectroscopy, the most powerful method for characterizing exoplanet atmospheres, to measure its atmospheric composition. Every piece of evidence we have about Proxima b's atmosphere is indirect: theoretical arguments, modeling results, comparisons with other planets in similar environments. There is an instrument that could, in principle, change this. The extremely large telescope, currently under construction at Cerro Armazones in the Atacama Desert in Chile, is designed to be capable of direct imaging spectroscopy of nearby rocky exoplanets, including, under optimal conditions, Proxima Centauri b. The ELT has a primary mirror about 39 meters in diameter, providing angular resolution far beyond anything currently available. With the right instrument configuration, it could, in principle, detect the spectral signature of Proxima b's atmosphere, including potential biosignatures that would indicate a biosphere. This is not science fiction. It is one of the ELT's specifically stated science cases. The telescope is expected to begin operations in the late 2020s. Proxima b is a primary target. If there is life on Proxima b, not certain, not likely, but possible, the ELT might be able to find the first evidence for it within the coming decade. BLC-1 did not find life at Proxima Centauri. But the attention BLC-1 brought to the system helped reinforce the scientific case for why the ELT's observation of Proxima b should be a priority. The false positive helped accelerate the search for real evidence. There are three ways to think about what BLC-1, Proxima b, and the broader Centauri system tell us about the search for extraterrestrial life. They sit on a ladder, conservative at the bottom, bold at the top. Each one is held by serious researchers. Each one has genuine supporting evidence. The conservative interpretation is that BLC-1 was a false alarm, and Proxima b is an interesting but uncertain habitability candidate among many. In this view, the BLC-1 story is important for methodology, but does not specifically elevate Proxima Centauri as a SETI target above other nearby stars. The signal was interference. It told us nothing about the actual radio environment of the Proxima system. Proxima b's habitability challenges are real, intense flares, possible atmosphere loss, tidal locking, and while not necessarily fatal, they are severe enough that other planetary systems may be more promising. The Centauri system deserves continued observation, but not exceptional prioritization. The supporting evidence for this view is the BLC-1 resolution itself. and the documented severity of Proxima Centauri's flare activity. The weakness is that it may be applying Earth-centric assumptions too aggressively. Life might persist under conditions we have not adequately modeled. This remains a common view on Proxima B's habitability among planetary scientists, though with acknowledged uncertainty. The moderate interpretation is that BLC-1 was an important near miss, and the Centauri system remains a primary SETI target for radio searches. In this view, proximity is a decisive advantage that outweighs the habitability challenges. Proxima b is in the habitable zone of the nearest star. Whatever its actual habitability, it is the closest possible location for a civilization whose radio emissions we could detect. At just over 4 light-years, signals from a civilization at Proxima Centauri would have been traveling toward Earth for only about 4 years. No other star offers this proximity advantage. Furthermore, the investigation of BLC-1 produced one of the most rigorous SETI methodologies ever published, the Shake framework. The Centauri system has been more carefully observed and more carefully screened for artificial signals than almost any other comparable target. The negative result of BLC-1 is, in a methodological sense, a kind of positive result. It tested the methodology and found a gap that was subsequently filled. This view is supported by the proximity advantage and the post-BLC-1 methodological improvement. The weakness is that habitability is genuinely uncertain, and proximity does not create life that isn't there. The bold interpretation is that the Centauri system, including not just Proxima, but also Alpha Centauri A and B, may be one of the most important astronomical targets of the coming century for both SETI and exoplanet life detection. In August of 2024, JWST detected what may be a planet orbiting Alpha Centauri A in or near the habitable zone. The detection used JWST mid-infrared instrument with a coronagraph to block the star's light and revealed an object more than 10,000 times fainter than Alpha Centauri A, at a separation consistent with a planet about twice the Earth-Sun distance from the star. Analysis suggested it could be a roughly Saturn mass gas giant in an elliptical orbit. Follow-up observations in February and April of 2025 did not detect the object, but simulations showed this was consistent with a significant fraction of possible orbits. The planet could have been too close to the star, from our viewing angle, to be visible in those observation windows. The findings were published in 2 papers in the Astrophysical Journal Letters in August of 2025, led by Charles Beichmann and Aniket Sanghai. The team plans additional JWST observations, including a window in August of 2026, to help verify the candidate's status. This potential Alpha Centauri, a planet, unconfirmed but not ruled out, adds a new dimension to the Centauri system's scientific significance. If it is real, it would be the closest habitable zone planet known around a Sun-like star. As a gas giant, it would not itself be habitable, but its proximity would make it an extraordinary observational target, and its gravity would shape the entire habitable zone of the system. This view is, for now, a minority among the astronomical community. The Alpha Centauri detection is unconfirmed, and the planetary interpretation requires more data. But it is taken seriously by researchers studying the nearest stellar systems, and it represents a potentially transformative shift in how the Centauri system is prioritized for future observations. There is a philosophical layer to this story that is worth sitting with. Why are we so drawn to the idea that our nearest neighbors might be inhabited? Proxima Centauri is close enough to seem conceptually reachable. A spacecraft traveling at 20% of the speed of light, the theoretical target for the breakthrough Starshot laser propulsion concept, would reach it in roughly 20 years. A signal, traveling at the speed of light, takes just over 4 years. There is no other star in the sky that makes interstellar contact feel even remotely feasible on human timescales. This proximity creates a cognitive pull that the scientific evidence does not necessarily justify. We want the nearest star to be inhabited because it makes the universe feel less lonely, because it makes first contact feel possible within a human lifetime, because it makes the entire project of searching for extraterrestrial intelligence feel like something we could actually accomplish. BLC-1 fed that pull. For a few weeks, it satisfied that longing, and the work of ruling it out, the patient, rigorous, honest science, is what makes the next candidate credible. We found a signal that looked exactly like what aliens might send. It wasn't aliens, and the process of proving it was. Aliens taught us more about how to find them, and more about the star we were looking at, than if we had simply moved on and never asked the question carefully. That is what science does. It takes the longing seriously, it applies the rigor, and it builds, from each honest negative result, a stronger foundation for the next search. Here is the strange thing about how BLC-1 has been covered in popular media. The coverage exists in 2 phases, and neither phase fully captured what was actually happening. The first phase was the December 2020 cycle, the leak, the social media explosion, the headlines about possible alien signals from the nearest star. This phase gave the story enormous reach. Hundreds of millions of people saw some version of the BLC-1 story. But it reported a story that the Breakthrough Listen team had explicitly not confirmed. The team was in the middle of ongoing verification work. The conclusion had not been reached. The headlines presented as a developing discovery what was actually an unverified candidate in the middle of a rigorous screening process. The second phase was the October 2021 resolution. 2 papers in Nature Astronomy, clear, peer-reviewed conclusions, one of the most rigorous SETI signal analyses ever conducted. This phase received a small fraction of the coverage of the first. Most people who saw the December 2020 headlines never saw the 2021 resolution. Let me tell you specifically what the popular coverage missed. The first thing it missed was the methodological significance of the Shake framework. One of the 2 Nature Astronomy papers, led by Shane Smith, described the characteristics of the signal and the overall search. The other, led by Sophia Shake, described the verification framework that ruled it out. This second paper is arguably the more important scientific contribution. It describes a rigorous end-to-end methodology for signal verification, and it will be cited as a foundational methods paper for years. Popular coverage treated it as a footnote to the "not aliens" conclusion. The second thing it missed was the specific technical nature of the intermodulation explanation. Saying it was interference creates the impression that BLC-1 was a simple, easily recognized fake. Intermodulation is not simple. It is a specific physical process. The mixing of 2 or more signals in a nonlinear electronic element that produces signals with properties fundamentally different from either source. An intermodulation product can have narrowband structure, a drifting frequency, and directional behavior that is genuinely different from the individual parent sources. Understanding why BLC-1 was so convincing requires understanding intermodulation. Almost no popular coverage described it. The third thing it missed was the significance of the harmonic analysis, the specific test that resolved the case. Searching for signals at harmonically related frequencies was not a standard part of the original Breakthrough Listen screening pipeline. The fact that dozens of similar signals were found at harmonically related frequencies in the same dataset, once you knew to look, revealed a class of interference behavior that future SETI searches now know to check against. That contribution was invisible in popular coverage. The fourth thing it missed was the JWST Alpha Centauri story. In August of 2024, JWST detected what may be a planet orbiting Alpha Centauri A. The detection received some media coverage. The follow-up, non-detections in 2025, and the subsequent modeling showing this was consistent with many possible orbital configurations, received much less attention. As of 2026, the status of this potential planet is genuinely unresolved, and most people following science news are unaware that the question is still open. The fifth thing it missed was the communication failure. The December 2020 leak happened because the story reached a journalist before the Breakthrough Listen team was ready to discuss it. The leak bypassed the scientific publication process entirely and forced the team into a reactive posture, neither confirming nor denying, attempting to convey scientific caution to a public that had already decided this was an alien contact story. The handling was about as good as it could have been under the circumstances. But the circumstances revealed a structural problem in how SETI candidate signals interact with the media cycle. That problem has not been fully solved. The next candidate signal will face the same challenge. In the years since the BLC-1 resolution, several developments have continued to change the picture around Proxima Centauri and the broader Centauri system. The first is the ongoing observation program. Breakthrough Listen has continued observing Proxima Centauri and has published the results of 39 hours of re-observation, confirming that no recurrence of BLC-1 has been detected. Beyond that, the program has continued its broader survey of nearby stellar systems using multiple telescopes, Parkes in Australia, the Green Bank Telescope in West Virginia, and the Mir-KAT array in South Africa. The Mir-KAT array is particularly significant, with 64 dishes operating together as an interferometer. Mir-KAT has both high sensitivity and the ability to localize signals on the sky in ways a single dish cannot. Its use for SETI surveys brings a qualitatively different capability to the search. If there is a real signal from Proxima Centauri within Mir-KAT's sensitivity range, the probability of detecting and verifying it is higher than at any previous point in the search. As of 2026, no new candidate signals from the Proxima Centauri system have been reported. The second development is the ELT science planning. The extremely large telescope in Chile is in its construction phase, with first light expected in the late 2020s. Among the highest priority science cases for the telescope is the direct imaging and spectroscopy of nearby rocky exoplanets, with Proxima Centauri b as a key target. If the ELT can separate the light of Proxima b from its star, spectroscopic measurements of the planet's atmosphere become possible. The detection of certain combinations of gases, oxygen and methane together, for instance, would be considered a strong biosignature, because the two react chemically and would deplete each other if not continuously replenished by some process, such as biology. The third development is the breakthrough starshot engineering work. The concept for sending gram-scale spacecraft to Proxima Centauri using laser propulsion has continued in study. Many fundamental technical challenges remain unsolved. The laser array power requirements, the survival of a tiny spacecraft through interstellar space, the communication link from over 4 light years. The concept remains ambitious to a degree that makes timelines difficult to state with confidence. But it has not been abandoned. It is worth understanding what Breakthrough Starshot actually proposes, because it represents the only currently conceived way humanity might get direct data from another star within a human lifetime. The idea is to build a vast array of ground-based lasers that would focus an enormous beam of light onto a tiny spacecraft, a gram-scale chip attached to a thin reflective sail. The light pressure from the laser would accelerate the spacecraft to roughly 20% of the speed of light over a few minutes. At that speed, it would reach Proxima Centauri in about 20 years, then transmit whatever data it gathered back across the 4+ light years, a signal that would take another 4 years to arrive. Every part of this is extraordinarily difficult. The laser array would need to deliver power on a scale comparable to a significant fraction of a major power plant, focused with a precision that pushes the limits of what is physically possible. The sail would need to survive acceleration forces thousands of times Earth's gravity, and then endure 2 decades of bombardment by interstellar dust and gas at relativistic speed. The communication link, sending a detectable signal from a gram-scale transmitter across 4 light years, may be the hardest problem of all. None of these challenges has been solved. Some may prove insoluble with any foreseeable technology, and yet the concept persists, because the prize is so extraordinary. If even a simplified version of Starshot were ever realized, it would give humanity its first close-up data from another stellar system, images of Proxima b, measurements of its atmosphere, perhaps direct evidence of whether anything lives there. It would transform Proxima Centauri from a point of light into a place. The fact that serious scientists and engineers continue to work on the concept, despite the enormous obstacles, is itself a measure of how much the nearest star matters to the human imagination. The fourth development is the continuing analysis of the Alpha Centauri JWST detection. The modeling work, done after the 2025 non-detections, has refined the range of possible orbits for the candidate planet. The observed pattern, 1 detection, 2 non-detections, is consistent with a specific subset of orbital configurations. Additional JWST observations are planned, including a window in August of 2026, when the candidate, if real and if the orbital models are correct, should be in a more favorable position for detection. The answer will come from data. There is one more dimension of the BLC-1 story that deserves attention, because it concerns not the science, but the question of what happens when humanity actually faces a possible detection. For decades, the SETI community has discussed what are called post-detection protocols, the agreed procedures for what should happen if a genuine signal is ever confirmed, who announces it, when, through what channels, with what level of verification. How do you communicate a discovery of this magnitude responsibly to a global public, through a media environment that rewards speed and drama over nuance and caution? These questions were not new when BLC-1 appeared. SETI researchers had been discussing them since the 1980s, producing draft declarations of principles about how a detection should be handled. But these discussions had always been somewhat theoretical. There had never been a candidate convincing enough to genuinely test the protocols. BLC-1 was a test, and it was, in important respects, a failure, not of the science, but of the communication process. The December 2020 leak meant that the public learned about BLC-1 not through a careful, verified, scientifically grounded announcement, but through a media report that emerged while the investigation was still ongoing. The Breakthrough Listen team was forced into a reactive posture. They had to respond to headlines they had not written, about a conclusion they had not reached, concerning a signal they were still analyzing. The result was a distorted public understanding that persists to this day. Many people absorbed the impression that something genuinely alien had been detected near the nearest star. Far fewer absorbed the eventual conclusion that it was interference. The gap between the excitement of the leak and the quiet of the resolution is exactly the kind of outcome that responsible post-detection protocols are designed to prevent. Since BLC-1, the conversation about post-detection protocols has become more concrete and more urgent. The experience demonstrated, with a real case, how easily the process can go wrong. It showed that the existing protocols were not robust against the simple reality of a leak. And it prompted serious thinking about how the field should prepare for the next candidate, which, given the expanding scale of SETI surveys, may not be far off. This is part of the BLC-1 legacy that rarely gets discussed. The signal taught the field not only how to verify a candidate technically, but how poorly prepared it was to handle the human and communication dimensions of a possible detection. Both lessons matter. A field that can verify a signal but cannot communicate about it responsibly is only half ready for the moment that matters most. And here is what makes the BLC-1 story truly remarkable. Not the signal itself, not the near miss, not the 2 years of investigation. What makes it remarkable is this. Imagine what would have happened if the investigation had gone differently, if the harmonic analysis had not been done, or had not found the other signals at related frequencies. If BLC-1 had passed every test without producing any definitive terrestrial explanation, if the Breakthrough Listen team had eventually been forced to conclude, in print, that they had found a signal from Proxima Centauri that could not be explained as interference, the announcement would have been one of the most significant events in human history. And there is a non-negligible chance that, without the harmonic analysis, a false confirmation could have followed. Not because the scientists would have been dishonest, because the pressure to confirm is real, and because without the harmonic analysis, without the framework shake built, the methodology did not yet have the tools to definitively rule it out. BLC-1 revealed the gap in the methodology at exactly the right moment. Not after a false announcement, not after a confirmation that then had to be retracted. Before any official announcement at all, during the period of investigation, at a time when the gap could be identified, documented, and filled. The time it took to build the framework, the 39 hours of reobservation, the harmonic search, the 2 Nature astronomy papers, was not time wasted on a false positive. It was time spent building part of the foundation that future SETI detections will stand on. Let that sit for a moment. One of the most important moments in the history of SETI may not be the day we find a real signal. It may have been the period when we found a signal that turned out not to be one, and took the time to figure out why, and built something better from what we learned. Not because failure is good, but because honest failure, carefully analyzed, is how the tools of science get built. And when a real signal comes, if it comes, the field will be better prepared for it than it was before BLC-1. That is the legacy, not an alien contact, a method, a standard, a better way of searching, but there is one more piece to this story. Because BLC-1 is not the only candidate signal SETI programs have investigated. And Proxima Centauri is not the only nearby star with a habitable zone planet that has received focused SETI attention. There are other systems, not as close as Proxima, but among the nearest to us, where planets have been confirmed in habitable zones, and where dedicated SETI searches are running with instruments that did not exist when the BLC-1 investigation was being conducted. And what those searches find, and do not find, raises a question about the search strategy that the BLC-1 experience made sharper. Are we looking at the right stars? Are we listening in the right way? That is a story for next time. Tonight, we did not just learn about a radio signal from the nearest star. We watched what happens when science does everything right, when it finds a candidate, investigates it rigorously, and publishes an honest negative result, and we watched what the popular media does with that process. The hype on the way in, the quiet on the way out, the gap between what happened and what the public heard. We saw Shane Smith, a young undergraduate, scrolling through over a year of archived radio telescope data. finding a narrow diagonal line in a frequency-time plot that would set off a 2-year investigation by one of the most sophisticated SETI programs ever funded. We saw Sophia Sheikh and her team build a verification framework, the harmonic analysis, the systematic exhaustion of non-alien explanations, the published methodology that has shaped how the field analyzes signals, a lasting scientific contribution from a signal that was never what it appeared to be. We saw a star, Proxima Centauri, receive more careful scientific attention because of a false positive than it had received in decades of routine observation. And we saw that attention producing new understanding of its planet's potential habitability, new prospects for direct atmospheric detection. And we saw the nearest stellar system, the place we have stared at for centuries, wondering, become more interesting rather than less, because of the honest work of people who were willing to say, "We thought we found something. We were wrong. Here is why we were wrong. Here is what we built, so we won't be wrong the same way again." Even now, the picture of the Centauri system is far from complete. We do not know whether Proxima Centauri b has an atmosphere compatible with life. The ELT may be able to address this in the late 2020s. Until then, the question is genuinely open. We do not know whether the August 2024 JWST detection around Alpha Centauri A was a real planet. Follow-up observations are planned. The answer has not arrived. We do not know whether any planet in the Centauri system is inhabited. This is the deepest question, and it may remain open for a long time, possibly until a direct observational test becomes possible. And we do not know when the next SETI candidate signal will appear, where it will come from, or whether the methodology built in response to BLC-1 will be sufficient to handle it correctly. These questions are open. The search continues, the instruments improve, the answers will come from data. There are a few things worth taking from this story that go beyond BLC-1 and Proxima Centauri. The first is that negative results are results. The investigation that ruled out BLC-1 produced a verification methodology, a new understanding of intermodulation as a SETI false positive mechanism, and a documented process for handling future candidates. This is genuine scientific progress. Progress that would not exist if BLC-1 had simply been dismissed as interference without careful analysis. The second is that how you search matters as much as what you find. The BLC-1 story is fundamentally about methodology, the criteria used to identify candidates, the tests used to verify them, the ways those tests can be fooled. Building better methodology is not less important than building bigger telescopes. It may be more important. The third is that premature announcements damage science even when they are not intentional. The December 2020 media cycle was driven by a leak the Breakthrough Listen team did not initiate. But the gap between what the public heard and what the investigation actually found is real, and likely permanent for most of the people exposed to the original headlines. Scientific communication is not just about publishing accurate results. It is about ensuring corrections reach the same audience as the original claims. The fourth is that proximity is not destiny. Proxima b's location in the habitable zone of the nearest star makes it a priority target. It does not make it inhabited. The discipline to hold that distinction clearly, to maintain scientific rigor in the face of the strongest possible cognitive pull toward optimistic interpretation, is what separates good SETI from wishful thinking. And the fifth is this. The most important scientific achievements are often invisible. The Sheikh framework will not make headlines. The harmonic analysis that resolved BLC-1 will not be remembered by most people who followed the story. But it is there, embedded in the methodology of SETI programs, helping protect the field from the mistake it came closest to making. So I want to leave you with a few questions tonight. What does it mean for the search for extraterrestrial intelligence that the most credible candidate signal in many years turned out to be terrestrial interference, and that 2 years of rigorous investigation were needed to figure that out? What does that tell us about the difficulty of confirming a real signal, if one ever arrives? If we found a real signal from Proxima Centauri tomorrow, with the instruments we have and the methodology we now have, are we actually ready? Are the communication protocols sufficient? Are the verification standards robust enough? Are the institutions prepared for what would follow? BLC-1 was, in a sense, a test run for the most important possible discovery in human history. It revealed gaps in our methodology, in our communication protocols, and in our institutional readiness. Those gaps are being addressed, but are they addressed enough? Sit with that. It is not a hypothetical question. If this story stayed with you, tell me in the comments which moment was the one that pulled you in. Was it Shane Smith finding the signal in archived data months after it was recorded? The 2-year investigation that turned a false positive into a landmark methodology paper? The realization that the nearest habitable zone planet is still deeply mysterious, even after decades of looking? Or the insight at the end that BLC-1 legacy isn't a signal, it's a method, a standard, a better way of searching that will matter on the day a real signal arrives? I want to know. And if you want more stories like this, real SETI science, told honestly, subscribe to Galaxy Pulse. We go beyond the headlines every single time. I will see you in the next one. We pointed a radio telescope at the nearest star. We found a signal that looked exactly like what aliens might send. It was an aliens. And the 2 years it took to figure that out, the rigorous, patient, careful work of proving what the signal was not, left us better prepared for the moment when the signal we find is something we cannot explain away. That moment has not come yet. We are more ready for it than we were before.